Once again, I welcome to the resource person Joseph Char sir. And also I welcome to all the participants. So this session we discuss about how the activation function will work, and followed by some demo session, right? Hello, sir, Joseph sir.
Sir, yes, sir.
Yes, sir. Can you continue, sir?
Okay, thank you, sir.
Thank you, sir. Thank you, sir.
Okay, so this session we will discuss about SoftMax function, how this SoftMax function works, and then how this SoftMax function derivatives is calculated, and how this loss function, what are the different loss functions available for a classification problem, and how these loss functions for a multi-class classification will be derived during back propagation. All these things we are going to discuss now. So assume we have a network like this. So in this network, we are giving the input value like x1, x2 up to xh, where x1, x2, xh are the different features to the artificial neural network. So we know that in artificial neural networks, we will calculate all these hidden layers are connected, which is fully connected. So x1 will be multiplied with this corresponding weight. And then, for example, suppose if you want to take the value of z1, we know that z1 is nothing but x1 w11 plus x2 w21 plus x3 w31 and so on up to xh wh1. So this is the value of z. So here this z is the first neuron in this hidden layer. So in order to calculate, assume this particular z1 represents one particular class. For example, it represents a dog class. For example, assume z2 represents a cat class. Assume z3 represents some other class called a zebra, and so on. So for our understanding purpose, we will take this number of features as n(h), but the number of neurons as 3, whereas we are going to predict only classes. We are going to predict only the 3 classes. Okay. So z1 is a weighted sum from this particular x1, x2 up to xh, and z1 is nothing but the weighted sum, and this z1 is passed to an activation function at the output layer. This is output layer. So this is passed in a multi-class classification problem. This z1 will be passed to an activation function, and that activation function is nothing but a SoftMax function. So this SoftMax function will give you an output, maybe consider some output as 85, like that. For example, the Z1 is producing an output. Assume Z1 is producing an output 85, and Z2 is producing an output 75, and Z3 is producing an output 20. Assume like that. Okay. So here, this SoftMax function is to give a probability value. For example, we already fixed this particular neuron Z1 to represent the class dog. Okay, so in order to identify dog, this 85, this 75, and this 20 value will be given as an input to this softmax function, and it will produce an output, and the output will be in the range between 0 to 1. Similarly, this particular output of this particular neuron is also giving a probability value within the range 0 to 1, and this is also giving a probability value within 0 to 1. And if you add this sum all together, you will get a value 1. So here, so our ground truth is y1, y2, y up to yh, and we will calculate the error for each neurons. So in general, what happens if you are taking a multi-class classification, problem, and if the number of classes is 3, then the output neuron at the final output layer, each neuron represents different classes, and the output of this particular neuron will be, the value of this particular neuron will be given as an input to the softmax function, and it will return a value or transform a value within 0 to 1. And if suppose if it is returning a value, for example, suppose in our case, suppose if I am passing an image called cat, if I am passing an image of a cat, and this will return, this represents dog, right? This represents dog, and this represents cat, and this represents maybe zebra. If you are passing a cat, then it will give lower probability in this particular neuron which represents dog. Maybe it will give a probability as 0.2, and here it will give you a probability as 0.2. Maybe here it will give a probability at 0.6. So which means you have higher probability in the neuron which is related to, which represents cat. Okay. So in our ground truth also, even though it is a cat, we will convert the label into one not encoding. For suppose we have 3 classes, if we are giving the input as cat, then the corresponding label will be 0, 1, 0. So 0 represents here the first 0 represents a dog, and the second element represents a cat, and the third element represents a zebra. So here the input label will be 0, 1, 0, which we will convert to a one-not encoding for this type of problem. So here y1 is representing 0 in this case, and yh here in this case it is 3 because we are considering only 3 class classification problem. So here it will be 0, but y2 will be 1. So this is our ground truth, which means this is the label which we get from the training data, and this is the output which we get from the neural network. So with the help of this particular value, we will calculate the loss. So loss E2 will be, so we know that E1 will be 0 because the ground truth will be 0 for Y1. So it will be 0. So multiplying anything with 0 will give you 0. So the error at this will be 0, and E3 will also be 0, but E2 will be minus 1 natural logarithm of O2. O2 is nothing but 0.6, which is the output of the softmax function. So you will, if you take this, you will get some value around 0.376. So this is what we call as loss. So we will calculate this loss, and our aim is to reduce this loss function. Our aim is to reduce this loss function. How we will reduce this loss function? We will reduce this loss function by back propagation. So in back propagation, we may use some optimizer like SGD, stochastic gradient descent, or stochastic gradient descent with momentum, or ADA grade, or ADA delta, or ADAM optimizer. We may use different optimizers. So the optimizer's duty is to back propagate this loss and to update this weight. So the reason behind why we are updating the weight is the output when we give a when we give cat as an input, we are getting an output as 0.6, and with the help of this output 0.6 y hat, we are predicting the error, we are calculating the error as 3.376. So in order to reduce the error, we need to back propagate, so that while back propagating, we need to reduce the error. We need to update the weights, right? So these weights, all these weights in between these layers has to be updated, and that is done with the help of an optimizer. So we have different optimizers called ADA, stochastic gradient descent, with momentum, ADA grade, and so on. So this is our error function. This is our error function, and this error function is specifically used for multi-class classification problem. Sorry. So if you are dealing with the binary classification, then the error function will be different. The error function can also be called as a loss function or a cost function. It depends upon the how we are giving the input, right? So suppose if we are giving only one input at a time, then this error function, we call this error function as a loss. Suppose if you are giving maybe if you are giving 10 images at a time, then you will calculate the loss. That time the loss function is called as a cost function. So in general, for a binary classification problem, the loss function is minus log y hat when y is equal to 1. What is y? Y is nothing but the ground truth, which we call as labeled data, right? Otherwise, if the label is not 1, if the label is 0, then the error function can be calculated as minus log 1 minus y hat. And this is used for binary classification problem. Suppose if you are using a multi-class, if you are dealing with a multi-class classification problem, in that case, this is also called as a binary cross entropy. So if you are dealing with, for example, suppose if you are dealing with a multi-class classification problem, in a multi-class classification problem, you need to calculate the loss, and the loss can be calculated by using the formula sigma I equal to 1, sigma minus I equal to 1 to k yi log yi hat. So we know that yi is nothing but the ground truth. Ground truth in the sense labeled value. And y hat 1 is nothing but the predicted value. Predicted value after using SoftMax. Predicted value after using SoftMax. Okay. So what is k? Here the k represents the number of classes. Number of classes in a multi-class classification problem. Okay. So here we are going to discuss how this loss function helps in updating a weight. So we are going to find the derivative of this loss function. So ultimately what we do is, in a back propagation, we will find the derivative of this loss function, and this derivative of this loss function will be forwarded to this next layers or the hidden layers, and in each layer we will calculate the derivatives, and then we will multiply them together to form to calculate a value, and this value will be subtracted by from the old value. For example, suppose if I want to update the weight here, for example, suppose if I want to update the weight here in this particular W11, suppose if I want to update the weight, I want to update the old value of W11. W11 is nothing but the weight of a particular link between the input or maybe between the two neurons. Okay, so here we need to calculate the new weight of W11 by subtracting the loss function by taking the derivatives of W11 old, and this is nothing but learning rate. So this is the general formula for modifying the weight for all these, modifying all the weights in between the neurons. Okay, so here W11 is the old weight, eta is the learning rate, and dou L by dou W1, we need to find the rate of change of weight with respect to the loss function. So this loss function will be this in case of multi-class classification problem, and this loss function will be this in case of a binary classification problem. So in order to calculate loss, in order to calculate this loss, what we do is we need to calculate the y hat. So this y hat can be calculated by using a softmax function. So how how to calculate the what is the formula for softmax function? So here the softmax function, the formula for a softmax function is we can write the softmax function formula as S of Zi is equal to e power Zi divided by sigma I equal to 1 to C. Okay, instead of I we can take it as K. K equal to 1 to C e power Zk. So this is the formula for softmax. So in order to calculate the new value for weight, we need to subtract the loss function with respect to that particular weight. But in order to calculate this loss function, you need this loss function for multi-class classification problem, which is this. But this y hat can be the predicted value of a particular record or a particular instance can be calculated by using this particular softmax function. So now we will discuss how this softmax function can be used, or else so in each and every step what we do is we will find the derivative of this. In order to find the derivative of loss function, we need to find the derivative of the error function with respect to the output, and this output is nothing but a softmax function. So we need to find the derivative of this softmax function with respect to that particular Zi and so on. So this follows a chain rule. Okay, this follows a chain rule. For example, suppose if you want to find the, for example, f of x is a function of x, and g of u is also a function, g of u is a function of u, then dou f by dou x is, dou f of x by dou x is possible, whereas dou g of u by dou u is also possible. Suppose if you want to calculate dou g of x, sorry, dou g of u with respect to x, it is not possible directly. So instead of that, what we do is we will go for a chain rule. First, we will calculate dou g of u with respect to dou u, and then we will calculate dou u with respect to dou x. Okay, in this manner, we will apply a chain rule. So this process, we are applying the same process here for calculating the loss function. So here, we know that the ground truth is the ground truth is y, which is nothing but a one code encoder. It can be either 0, 1, 0, but only one element will be represented by 1, and all other elements will be represented as 0 in a one code encoding, which means this class, the corresponding element represents dog class, assume like that. This is a cat class and this is a zebra class. So for a particular instance, the output vector will be, or the one hot encoding will be 0, 1, 0, which means that particular instance is nothing but a dog. So we know that Z is nothing but a function of Z1. From this particular diagram, we know that Z1 is a function of Z is a function of Z1, Z2, and Z3. Okay. So when we take an activation function, for Z of 1, then we will get e power Z1 divided by e power Z1 plus e power Z2 plus e power Z3. Suppose if you are taking an activation function with respect for Z2, Z2 is nothing but the second neuron in this in the hidden layer, which represents dog. Okay, so E Z2 divided by E Z1 plus E Z2 plus E Z3. Similarly, activation function, when we are applying activation function on top of Z3, you will get e power Z3 divided by e power Z1 plus e power Z2 plus e power Z3. So another important thing is, in order to calculate the softmax function for Z1, we need the term, Z1, Z2 as well as Z3. We need the combination of all these output of Z1, Z2, and Z3. So in general, we can write as S of Zi. If you want to calculate the activation softmax function, if you want to calculate the softmax of a particular neuron, then we can write it as e power Zi divided by sigma a equal to 1 to c e power zk. So this is the general form of a sigmoid function. If you want to calculate the sigmoid function for first neuron, you can apply this formula. If you want to calculate for second neuron, you need to apply this formula. For third neuron, you need to apply this formula. So as I already discussed, the sigmoid function is nothing but a probability. It is a probability distribution function, right? So in that case, if you add this sum of activation function of Z1 and activation function of Z2 and activation function of Z3, you will get the term output as 1. So that is why it is called as a probabilistic approach. So here first what we are going to do is, suppose we want to find the derivative of softmax function. Suppose assume that we want to find the derivative of softmax function at z1. Assume like that. So from this we know that z1 is nothing but a combination. We can calculate the softmax function only with the help of z1, z2 and z3. So this is nothing but s of z1, s of z2 and s of z3, because activation function of z1 depends upon all these activation function terms. Okay. When we take a particular derivation of a softmax function with respect to z1, we will get e power z1 divided by e power z1 plus e power z2 plus e power z3. If we want to find the derivative of softmax function with respect to z1, then this can be written as, we know that for example, suppose f of x, f dash of x divided by, f of x divided by g of x. We have a function like this and we want to find the derivative of this function. Then you will do f dash of x into g of x minus f of x into g dash of x divided by g of x the whole square. So applying this formula while finding the derivative, we will get e power z1, because we are taking the derivative of e power z1. E power z1, derivative of e power z1 is nothing but e power z1, because we are doing derivative with respect to z1, into, we are taking this term as it is, so into e power z1 plus e power z2 plus e power z3 minus, now we need to take we need to keep this term as it is, e1 power z1, and we need to take the derivative of this, which is nothing but you will get e power z1, because this term and this term will give 0. Okay. Divided by e power z1 plus e power z2 plus e power z3 into e power z1 into e power z2 into e power z3. So we are applying this formula. We are applying this formula to find this derivative. Okay. And then next what happens, we know that we are replacing this sigma terms, we are replacing this summation as a sigma. Assume like this. We are replacing this summation as sigma. So you will get e1 z1 sigma divided by sigma sigma. So this can be written as e1 z1 divided by sigma. Here also we have another term. Okay. Minus e1 z1 e E into Z1. Okay. So we are replacing this this term with a sigma. Okay. So E1, sorry, E is Z1 sigma minus E Z1 into E Z1. You will get a term like this. So this can be written as E power Z1 divided by sigma. You are taking E Z1 as common. So you will get sigma minus E power Z1. And in denominator, you have two sigmas. I'm rubbing this, okay. So next what happens, you are taking this term separately. So which is nothing but E power Z1 divided by sigma into sigma minus E power Z1 divided by sigma. So you are splitting these two terms separately. So now you get E power Z1 divided by sigma is nothing but S of Z1. We already discussed that, which is nothing but Z. This is nothing but S of Z1, right? And then this can be rewritten as 1 minus E power Z1 divided by sigma. So this can also be rewritten as S of sigma 1. So finally we get S of sigma 1 into 1 minus S of sigma 1. So this is the derivative of a particular sigmoid function. Okay, this is the derivative of a function or a particular sigmoid function with respect to Z1. So this is the derivative. Suppose if similarly, suppose if we similarly this, if you look at this particular formula, it is very clear that derivative of sigmoid function with respect to Z1 is equal to S of Z1 into 1 minus S of Z1. And with this we can clearly say, similarly for S sigmoid of Z2 with respect to Z2, we can write it as sigmoid of Z2 1 minus sigmoid of Z2. And similarly, we can write for sigmoid of, sorry, not sigmoid, softmax. Okay, softmax of Z3 divided by Z3 is equal to S of Z3. S of Z3 is nothing but softmax of Z3 into 1 minus softmax of Z3. So we can write like this. We can write like this only if the numerator value and the denominator are both equal, which means I is equal to K. Okay, we can write only if I is equal to K. Okay. Another derivation what we are going to do is, suppose if we want to find derivative of z1 with respect to z2. In that case, what happened? In that case, we know that derivative of e power z1 divided by e power z1 plus e power z2 plus e power z3 rho z2. So when we do derivation with respect to z2, when we do derivation with respect to z2, then what happens? This particular numerator will be 0. So 0 into anything will be 0 minus, you are keeping this term z1. We are applying the same formula here. Whatever formula we are applied previously, we are applying the same formula. Into, when we derive with respect to z2, only this term will be retained, all other term will be 0. So into e power z2. So this can be written as, in general, if you are doing a softmax derivation with respect to z2, where I is not equal to k, then you will get minus e power z1 into e power z2. This is for 1 and 2. For example, so similarly, if you are taking dou an activation function z of I with respect to z of k, where k is not equal to I, you will get minus e power z I e power zk. So this is the general term. Okay. So when we derive this, but when we take a derivative of this particular sigmoid function with respect to different values of z, we will get two outputs. So generally, we can write this output as dou s of zi. We are doing the derivative of softmax function with respect to zk. Suppose if I is equal to k, then we will get the first result as s of zi into 1 minus s of zi. Suppose if I is not equal to k, then you will get minus s of zi into s of zk. So this is the derivative of softmax. Okay, why we need derivative of softmax? Because during back propagation, at each layer we need to take the derivative with respect to that particular weight. So in order to take derivative with respect to that particular weight, it is not directly linked. You need to apply a chain rule. So in order to apply a chain rule, you need this in between. So we are applying softmax function, right? So you need this. Similarly, so here I have find the derivative in this particular location. In this particular layer, I have find the derivative, and the derivative is like this. Okay. Here also you need to take the derivative of the loss function with respect to this particular weights. You need to take the derivative of the loss function with this with respect to this particular weights W1, W21, and W31. Okay. So for that, what we do is we need to calculate these. We need to calculate the total error. we need to calculate this total error. So we know that the total error is nothing but the total error E is nothing but E1 plus E2 plus E3, where E1 is nothing but the error which we get from E1 is nothing but the error which is due to the first neuron, right? Y1 log O1. We have already discussed this. If you look at this diagram, you can understand. So this is the error with respect to the first neuron, error with respect to second neuron, and error with respect to third neuron. And why we are using this error function? Because here we are using multi-class classification problem. Okay. Similarly, E2 is equal to Y2 natural logarithm of O2, and E3 is nothing but Y3 natural logarithm of O3. Okay. So in general, what we can do is we can write this, we can write it as E is equal to O of, we can write it as E is equal to Y of I natural logarithm of O of I, where I starts with 1 and it will go up to the number of classes. So this is our loss function. So we need to find the derivative of this loss function with respect to W1. Okay. We need to find the derivative of this loss function with respect to W1. Why we need to calculate the loss function with respect to with respect to W11? Because we need to change this weight. W11 we need to change. Okay, but this can be done. This cannot be. We cannot do partial differentiation. We cannot do it directly. We can do with the help of a chain rule. So dou L divided by this can be done with the help of dou L divided by dou, applying chain rule, right? Dou L divided by dou O of I, because L is a function of O, right? And then dou O of I with respect to Z of K. And then dou Z of K with respect to Z of O, Z of O with respect to dou W 11. So we need to calculate in this manner. Okay. So for that we need to calculate this loss function, derivative of this loss function with respect to softmax. So for that, what we do is we will apply, we will take this loss function and we will do derivative with respect to the softmax. So here we need to do dou L or else dou E with respect to dou ZK. So we know what is the error, right? We are writing the error as minus sigma I equal to 1 to H Y of I log O of I divided by dou of ZK. So this can be written as minus, we are taking the summation term outside, minus sigma I equal to 1 to H dou of y of I natural logarithm of O of I divided by dou of zk. So we know that y of I is nothing but a ground truth, right? We know that y of I is a ground truth, so it does not have, it will not change with respect to any derivative, right? With respect to k, z of k. So we can write it as minus sigma I equal to 1 to h my y y and then derivative of natural logarithm of O of I divided by dou of zk. So this, in order to find this term, we know that the output is a function of O of I. So it cannot be done directly. We are applying a chain rule. So by after applying the chain rule, what we get is equal to minus sigma I equal to 1 to h y of I dou ln of O of I, natural logarithm of O of I by O of I into dou of I divided by dou z of k. This is what we get. So we know that derivative of log x is nothing but 1 by x. So by applying this, we will get minus sigma I equal to 1 to h yi divided by O of I. So this term is nothing but log x. Log x is nothing but 1 by x. So which is nothing but 1 by O of I into dou O of I divided by dou z of k. Okay. So next we know that we have already calculated this term, right? We have already calculated this term. If you look at this in our this one, see here, we have calculated. No, we have calculated this. Dou softmax function of zi divided by dou zi is nothing but it will give two values. Depending upon the value of I and k, you will get two values. Okay. So when you replace this, you can replace that here. So after replacing, what you get minus sigma I not equal to k h y of I divided by o of I into, when I is not equal to k, we have the term minus o of I into o of k. Similarly, when I is equal to 1, we get the term as y of k divided by o of k into o of k 1 minus o of k. Here we are replacing this o of I by o of k because I is equal to k. Now we get we are going to cancel this term and this term. We are cancelling this term, so we get minus sigma I equal to k to h y of I into O of k. Similarly, this term can be replaced as plus y of k into 1 minus O of k. So here we are doing a simple trick. We know that the summation, that is the summation of I equal to 1 to h y of I is equal to 1, which means the output of when we combine or when we add the summation of all the output layers softmax function, you will get the answer 1, right? So what we are going to do here is you can replace this by you can replace this particular term as sigma, sorry, you can replace this term as O of k into this term can be replaced as 1 minus y of k, because this is not equal to k, right? This is not equal to k. Since it is not equal to k, we are subtracting that particular output value with this 1, so you will get the summation of remaining terms plus here you have minus y of k minus y of k O of k. So this can be when you multiply this minus the, if you multiply this term with minus, you will get the output as O of k minus O of k y of k minus y of k minus O of k y of k. So here these two terms will cancel each other, so you will get O of k minus y of k. So this is the derivation of dou E with respect to this softmax dou zk. Okay. So in order to calculate this, we are using a chain rule, and in that chain rule, we are using the derivative of softmax function. So from this, what we can do is we can update the weight directly. Okay. So in general, what we can do is dou E divided by dou Z3. This can be replaced as dou O3 minus Y3. So if you want to find the derivative of a particular loss function with respect to Z3, then you just subtract the ground truth with the predicted value. Okay, so this can be done. And later on, what happens if you want to change if you want to change the weight function, then you can multiply this with you can multiply this and you can take the derivative of this weight function z with respect to z1, and then you can change the up, and you can find the new value of weight, and with the new value of that weight we can change the old value. You can find the derivative of loss function with respect to rho of 1 1, and with the help of this you can change the, you will get the new value of weight by subtracting the old value. Okay, where eta is nothing but the learning rate. So next what we do is we will write a program. We will write a program for calculating or predicting the, to predict whether a given particular, see, the thing is what we are going to do as a demo is we have some set of images, and these images is nothing but images of x-rays, where uh, images of three different kinds of peoples are available. For example, the people who is affected with COVID, the people who is having viral pneumonia, and as well as normal people. So we have three classes, and with the help of these three classes images, we are going to predict given an input image, we are going to classify that particular input image to a particular class. That is what we are going to do. So this can be done with the help of Google Colab, or else you can also install Jupyter or any of these tool. With the help of this IDE, we can execute this program. Okay. So I will quickly explain you this program, as well as I will share you this code as well as the data, sample data. You can try it by yourself. Okay. Okay, I will try from my email ID. Okay. So what you need to do is you need to open a Google Colab. Okay, in this Google Colab, I have already executed this particular program. I will tell you the steps how to do this particular program. Okay. So initially what you need to do is once you open a Google Colab, you need to type the programs, and the data required for this program is nothing but an input image. So here the input image is, I have stored this image in this Google Drive, in my Google Drive, and with the help of this particular here mount Google Drive. So if you click this particular icon, it will ask you for whether you need to mount your drive to this particular collab, and you will get a activation code, and you need to type that activation code to mount your Google Drive to this particular collab. So I have already done this, and so here what happens in my image, in my data set, you can see. So here is my data set. So here what happens, you have a data set with three classes. whether it is a COVID. So you have a COVID images, you have around some hundreds of COVID images. Also, you have some normal images, and also you have some images related to viral pneumonia. Okay. So what I have done is I have splitted the images into three different folders, and the three different folders are train, test, and single prediction. So train is for training the neural network, and the test is for testing the network while training, as well as the single prediction is finally once you train the model, you need to predict, right, whether you are getting a correct output or not. For that validation purpose, I am using a single prediction. From this, I am going to pass one image, and I am going to check whether that is predicting correctly, whether the model is predicting correctly. So, okay. So here you have uh, the first, this particular import TensorFlow as a TF is nothing but a importing the TensorFlow libraries, because we need TensorFlow libraries for executing this particular for creating a neural network. We use some libraries, right? And these libraries or these tools will be present in this particular TensorFlow libraries. And before the next thing is we need to pre-process the data. In order to pre-process the data, we are using Keras libraries, which is also a part of TensorFlow 2.0 version. After from TensorFlow 2.0 version, everything is clubbed, right? The Keras is also a part of TensorFlow. So here, if in this Keras library you have some image data generator. So what is the purpose of image data generator names? With the help of this image data generator, you can convert this image into an RBG image, and also this image we can do some pre-processing with that image, like rescaling, rotating with shift, because the main purpose of this image pre-processing is to since we are not having enough data, we have only some 250 data for training purpose. We need to modify, or we need to change the angle, or else we need to rotate the image, or else we need to change the height, or else we need to shift the images to some point. Uh, we are doing some pre-processing, and this pre-processing is done with the help of this image data generators. So this image data generator is having some different attributes, and I'm giving some values to these attributes. So you can also read this following link, which will help you to understand better about image pre-processing. Okay. So what happens, I am first dividing the data set, what I need to do for training data set, how I need to do some pre-processing, and for testing data set, how I need to do some pre-processing. All this will be given in this part of code. So here what I am going to do is, since I have already discussed to you, we need to mount our data set. You need to store all your data set in your Google Drive, and you need to mount your Google Drive to this particular Google Colab, right? So after mounting, you will get a path, and that path has to be copied here. So this is nothing but the path of the trained data set. From that, you are converting the image into different into a fixed size of 64 of height to 64 and width 64. Okay. And the number of batch size is 16. So batch size in the sense, we know that while training a model, we need to pass, we can pass all the images to the network, so that it will finally calculate the loss, and then the loss will be, and we need to update the weight with the help of an optimizer. That is the normal process. That is what we call as gradient descent. But in stochastic gradient descent, or with momentum, or ADA, or ADA grade, or ADAM optimizer, what we do is we are going to divide this entire data set into small sections, and each sections will be having some number of records. That number of record is what we call as a batch size. So batch size of 16 means I am going to split the data into a group of 16 records. And then since we are using categorical classification, my class mode is nothing but a categorical. So the same thing is happening here in test data generator also. In test data also, what we are doing is we are going to rescale the image. Rescale the image means, for example, suppose if you take an image, if you take a particular pixel, that pixel point will be having some numbers between 0 and 255. So here rescaling is very important, because I am dividing the entire pixel, each and every pixel value by 255, so that I will produce a number between 0 and 1. So this is also called as some rescaling, or normalizing. We can say like normalizing. Okay. So the purpose of doing this is for better calculation, for speedy calculation. Or else what happens, if you multiply a huge number with a huge number, then what happens, it will take lot of time. In order to avoid that, we are going to rescaling that between 0 and 1. Okay. And the target size is also 64, batch size is 16. So what to do with test data and what to do with train data, we have already mentioned in this pre-process. And next, what we are doing is, we are, with the help of this TensorFlow, we are adding this, we are creating a sequential pipeline. Sequential pipeline means, I've already discussed you about the convolution neural net, convolution layers, right? In convolution layers, we can add different convolution layer. In between convolution layer, if you want to add a max pooling layer, you can also add a pooling layer. So all this together forms a sequential flow, right? Only after completing convolution layer 1, you can proceed with convolution layer 2. Only after completing convolution layer 2, you can proceed with convolution layer 3. So the pipelining is like sequential. That is why it is called as a sequential. So that is done with the help of this sequential class. In that sequential class, we also have a method called add. This add is nothing but to add the convolution layer. So if you look at this particular command, you can see CNN is nothing but the our model name. CNN is nothing but the object, sequential object class, the sequential class objects. Okay. So CNN is nothing but the object of the sequential class, and with the help of this object, we are going to add different layers, like a pooling layer, or a convolution layer, or different layers. Okay. So first, we are adding a convolution layer, and this convolution layer is taking the filter of size 32. So you have 32 filters, and the size of each filter is 3 cross 3, and I am using a padding as valid, and also I am using the activation function relu. So we already discussed about a relu activation function. So relu activation function means the output, if the pixel value is less than 0, it will be treated as 0. It will transform to 0, or else it will transform to the corresponding value of the pixel itself. And the input to this particular convolution neural network is an image of size 64 into 64 into 3. So we have, even though we have 250 images for training set, these images are of different dimensions. But in pre-processing, we are changing all the images size to 64. Next, what we are doing is, we have added the first convolution layer, and the first convolution layer is having 32 filters, and the size of the filter is 3. Here we are not using any padding. That is why I am giving it as valid padding, and I am using the activation function as relu. And in the next layer, what I am doing is, I am going to add a max pool. I am going to add a max pooling layer. So the size of the filter is 2 cross 2 in pooling layer, whereas the stride is 2. See, here we are not mentioning any stride, which means if the stride is not mentioned, then the default value of 1 will be taken into account. Okay. Or else you need to mention the stride value if you want to change the default value. So here, cnn.add tf.keras.layers of max pool of 2D pool size equal to 2 means I'm talking about the filter size. Okay. And the stride is 2. So this is my convolution layer. This is my pooling layer. And here also I am adding one convolution layer followed by a pooling layer. Okay. So in the second convolution layer, we have 64 filters, and the size of each filter is 3. I'm also using activation function as relu. I'm not using padding, any padding. So if we are not mentioning any padding means that default padding of valid will be taken into account. Also, I'm adding a pooling layer in this particular sequential pipeline. So the pooling size is 2 and the slide is 2. So here you can change the numbers. These are what we call as hyperparameters. The size of the filter, instead of 32, you can give it as 64. Instead of kernel size, instead of 3, you can give it as 5 cross 5 and so on. So these are hyperparameters. Hyperparameter in the sense you need to sit and try and find out the good experiments. Okay. So after this, adding kernel, after adding first convolution layer and then max pooling layer and then again convolution layer and again max pooling layer, I'm just flattening this activation map, whatever is coming out of this particular pooling, second max pooling layer. Okay. So here, if you look at this particular first convolution layer, you can see the input image, the size of the input, the size of the image is given only at the beginning of the first convolution layer, whereas the size is not given in the next layers because this is the tool itself will understand the shape of the activation map and then it will be given as an input. That is not a problem. So after flattening, what happens, all the features will be flattened into a single dimension. And then after that, what I'm going to do is I'm going to give this flat input features, whatever features I am extracting from convolution layer, I'm going to give that feature as an input to the artificial neural network. So here, this is to create an artificial neural network. Here, the artificial neural network consists of 128 neurons. So this 128 neurons will be connected, fully connected with all these flattening pixels. So each and every pixel in flatten will be treated as a neuron. Okay. So after this, we are giving this to an artificial neural network, and the size of this, the number of hidden layer is 1, whereas the number of neurons in the first hidden layer or the hidden layer is 128. And here also we are using ReLU activation function. Why I am using ReLU means you can also, this is also an hyperparameter. You can tune, you can use, instead of ReLU, you can also use different activation functions like SoftMax, different activation functions like a SoftMax or a sigmoid or ADA hypertangent or any other activation functions you can use. Okay. But mostly everybody is using ReLU because ReLU will give good performance. And then finally, this hidden layer is connected to the output layer, and the output layer is having the number of unit as 3. As I already discussed, here we are going to classify only 3 classes. So since we are using only 3 classes, the number of unit in the output layer will be 3. And as I already discussed with you, the activation function at the output layer, if you are using a multi-class classification problem, then it will be a SoftMax function. But if you are using a binary class classification problem, then the output layer activation function will be a sigmoid function, because we know that sigmoid function will always give the values between zeros and ones. And if you, for example, probability between 0 and 1. So if you get a value 0.2, then it means it belongs to 0 class. If you are getting a probability value of a 0.7, then it means that it belongs to class 1. Okay. So in that case, you can give, if you are dealing with a binary classification problem, you can deal with, you can replace this SoftMax with a sigmoid function. So here, what happens here, I am, okay, this process is complete. So the structure of the network is created with the help of this sequential class. In sequential class, I am going to add one by one. First, I am adding the convolution layer. Second, I am adding the max pool layer. Again, I am adding the convolution layer. Again, I am adding the max pool layer. And then I am just flattening. And then I am adding the artificial neural network. And then I am adding this dense, that is artificial neural network. And then the output layer with 3 neurons is also added. And then finally, what we are doing is we are compiling this model. What you mean compiling this model means, we know that In a forward propagation, it will calculate the weighted sum, it will apply the activation function, and it will finally predict the output. And based on that output, you will calculate the loss function. And based on the loss function, you will, if the loss function is too high, or if the loss function is not reaching, the global, if the loss function is not reaching the global minima, then you will keep on do this forward and backward propagation. So this forward and backward propagation will be done with the help of this optimizer. So here in this case, I am taking the optimizer as SGD. SGD means stochastic gradient descent. You can also replace that with the ADAM optimizer or ADA grade or a stochastic gradient descent with momentum or any other optimizer. So the purpose of this optimizer is to update the weight in backward binary class classification problem. The loss function will be binary cross entropy, whereas if you are dealing with a multi-class classification problem, the loss function will be categorical cross entropy. And the metric I am dealing with here is accuracy. So in each and every term, since we are taking the batch size as 16, for the first batch, what happens, you are calculating the error, and that error is calculated and it will throw some accuracy. For that, I am using this metric as accuracy. So after this, what I am going to do is, with the help of a fit function, I am going to fit this. I'm going to execute this model, whether this particular data set is fit with this particular model or not. I am going to check it out. So with the help of this CNN.fit, I'm going to take this X as training set. So we already discussed that a training set is nothing but a combination of training set. You can, if you look at this training set is nothing but you have some images inside this training set, and from that images you are randomly choosing a 16 images, and you are going to train the model. Okay, so in each epoch, what happens in each epoch, so here I am going to give only one epoch, which means first epoch means suppose if you have 100 if you have 1000 data set, if you are forwarding 1000 data set, and then you are calculating the loss function, and then you are doing a back propagation, that represents one epoch. Suppose if epoch can be divided into batches, then we call that as iteration. So in each iteration, you will calculate the loss function, and you will back propagate with an optimizer to reduce the weight or to modify the weight. Okay, so so here I am going to train the model. When I start training the model, what happens is, first 16 images will be forwarded to the network. It will pass through different convolution and max pooling and whatever artificial neural network I have formed. It will pass through that, and it will calculate the output, and with that the help of that output, it will calculate the loss function. And with the help of that loss function, if the loss is very high, you can see it will calculate the loss function, and based on the loss function, it will back propagate with an optimizer. So here you can see my data set is having 251 images, and out of this 251 images, I am dividing these images into 16 groups. So each group will have some 16 records, right? So the first time what happens, I am passing the first batch. In first batch, it is calculating the loss, and it is calculating the accuracy. And after completing this first iteration, it will also calculate the loss, and all this loss, and this loss will be our objective is to reduce this loss, and this can be done with the help of the optimizer. So it will take some time. That is why I've given only one epoch. Okay, if you are giving more epochs, then what happens, it will take more time. So we will discuss this later, what exactly happening here in this particular thing. So here what happens, if you look at this, 16 out of 16, which means our batch size is 16, which means out of 251 records, I am dividing the batch size into 16. So in first iteration, it is calculating the accuracy, and then it is calculating the not only accuracy, it is also calculating the loss. So if you look at this, you can see that training loss is nothing but 1.0803 and the validation loss is 1.1573, whereas our accuracy of the training set is 0.4 and the accuracy of the testing set is nothing but 0.27. So as the training continues, you can see this will keep on, the accuracy will improve and the loss will reduce. Okay. But unfortunately, we are not having enough data set to build this model, a perfect model, because if you are going for a deep learning model, then you need a huge data in the sense you need huge data. Also you need a lot of computations. That is why here we are, that is why all of them are going for GPUs, or you can also in also Google Colab, in also this Google Colab, you can go for a paid version of Google Colab where you will be provided with the GPUs. So according to your requirement, what happens, you can you can you can you can change the slabs. Like if you want more GPUs, then your premium will your the amount you need to pay to the Google will be changed accordingly. See here, so after one epoch, it is showing this. Suppose if I want to change this epoch size to, instead of 1, if I want to change it to maybe some 10, then what happens? It will train for 10 epochs. So normally 10 is minimum, because you have to give 5,000 and 10,000 epochs in order to train and extract the features. Okay. So first epoch is over. The second epoch is going to complete. So this is 9, this is 10th batch, 11th, 13th, 15th, and 16th batch. So the second epoch is over. So if you can see the accuracy is keep on increasing in each epoch. Okay. So another type of thing is you can also save the model. So you have here in this whatever we have constructed with two new convolution layer and two max pooling layer. Some network we have constructed, we can save the structure of that network by using this command called cnn.save, so that what happens, your network structure will be saved. For example, suppose you are doing experiments by changing the networks. See, a number of convolution layer and number of pooling layer and a number of hidden layers, number of units in the particular layer, it all, everything is a hyperparameter. So you need to keep on change, you need to do some experiment. So for each and every experiment, your accuracy and the loss will be reduced, right? Your loss will be changed. So you can record that by saving network with the different names, so that you can have some comparison later. So here you can see this it is keep on fluctuating, because this is due to this stochastic gradient descent. The stochastic gradient descent is an optimizer which is having noise. That is why the next version of stochastic gradient descent with the momentum, which will smoothen this noise. So you have different optimizers. You can try out with the different optimizers so that your accuracy and loss will be changed. So next, what happens when you save this model? You can save this model and then from this model you can also take the summary. The summary here, in the sense, it is showing how many layers are there and how many. So we have discussed about, we have implemented two convolution layer that is represented here. Also we have implemented two max pooling layer, which is also represented here. And then we have implemented a flattened layer, and then we have implemented a dense layer with 128 units, and also we have a dense layer with a 3 number of units. So this dense layer is what we call as an output layer, and this is flattening. And so this is the network architecture, and the summary of this network architecture you can get by using the summary function. Okay. So here you can see the activation, the accuracy is 0.57 after 10 epochs. So if you change it, if you keep on change means by different hyperparameter, if you tune the hyperparameter, your accuracy will get improved. Or else what you need to do is you need to increase your data. You need to increase your training data. Here we are dealing only with 250 data, right? So you can save the data, and then you can save the data by using save function. And also you can, suppose in later case, if you want to open this model, whatever you have saved, you can use this module called a load Keras module. We have a class called a load model, and with the help of that load model, you can load the model. Okay. And then with the help of this summary, you will get the summary of this particular network. So that is why I told you previously, you have convolution max pooling, and so on. So now you tell me different parameters. Before at the end of the first session, I gave you some question like how many learning parameters are available, right? So how will you calculate the total number of learning parameters? So if you look at this particular input, the input image is 64 cross 3, right? The image is 64 cross 3. So in that input image, we are using how many filters we are using in the first convolution layer. In the first convolution layer, we are using 32 filters, and the filter size is 3. So 3 cross 3 cross 3. So filter size is 3 cross 3, height and width is 3 cross 3, whereas the depth is the depth of the input, which is 3 in this case. So 3 cross 3 cross 3 is the total number of learning parameters for one filter. Not only that, we also have a bias added to that. So 3 cross 3 cross 3, which is nothing but 27 plus 1, which is nothing but 28. So 28 into 32, which will give you around which will give you 896. So that will be the parameters, that is the learning parameters. So for that much amount of weight, you need to change that much amount of weight in back propagation in that particular convolution layer. Okay. Similarly, in second convolution layer, you have training parameters of 18,496. So why it is so? Because in the second convolution layer, you are using 64 filters. So if you are using 64 filters and the size of each filter is 3 cross 3, here in this case, the depth of what is the depth to this what is the input to this particular convolution layer? The input to this particular convolution layer is a channel of size 32. So the number of training parameters in this particular second convolution layer is 3 cross 32 plus 1 into 64. Okay. 3 cross 32 plus 64. 3 cross 3 cross 32 into 64. Okay, so you have 18,432, but 18,432 plus you have also have 64 filters. Okay, so you need to add 64 bias to that. Okay, so you have different parameters at a different input layers. So the main purpose of using convolution layer is to reduce the number of training parameters. If you are using an artificial neural network, in artificial neural network, each and every neurons is connected to all other neurons in the hidden layer or all other neurons in the next layer. So what happens if it is fully connected, then the number of weights has to be trained will be increased. So that is avoided in convolution layer, but because in convolution layer we use a concept called weight sharing. So even though we have weights, we need to update the weights. Some of the weights will be shared with some of the neurons. Okay. That is the reason why the number of learning parameters in convolution layer is lesser when compared to the dense layer. So finally, what happens, what we are going to do is we are going to take one input, one particular image from this particular test image, which represents one particular folder. And from that particular folder, you have a image with the name COVID underscore example underscore JPG. And when you execute that, what happens, it will take that image, it will convert that image into 64 cross 64 cross 3 with this particular set of code. And then what happens, we are going to predict that. So after predicting, what happens, we get whether that particular image is a COVID image or not. So in this case, we have taken that image as COVID. Suppose if we, instead of taking this image, if I am taking some other image, I am taking some other image, maybe if I am taking a normal person's image, whether I want to check whether that particular person is having a COVID or not, whether it is predicting, whether the model is predicting correctly or not, then maybe we have some less accuracy, so it may not predict correctly. Okay. See here. The first time I am passing the COVID image, it predicted correctly. But the second time, if I am passing the normal image, it is predicting as viral pneumonia, because we know that our model is not a good model, because it is having accuracy only 58%, and it is having a huge loss. And this can be avoided. This can be avoided by training the model with a huge sample of inputs. Okay. So with this, we can wind up today's class. If you have any doubt, you can ask me. If you have any doubt, you can ask me. Okay. Yes, Sureka.
Hello, am I
Yes,
audible,
ma'am.
sir?
Yes,
Okay.
yes, yes.
So, very nice session, sir. Actually, I had been hunting for so many YouTube material like for the intro of the CNN and all, but to this level, no video I have ever occurred. And all the stages were explained very nicely. That was a wonderful thing. One more difficulty I had, sir, actually, I'm working with this CNN, and just I'm planning to work with CNN. My
Okay.
work is actually I'm having some MRI images of a fruit,
Okay.
and the MRI image before after MRI imaging, I'm going to go for the physiochemical test in the laboratories. So I will be having an Excel sheet like the data that I will be sending that as a target values.
Okay.
Now, how much is the size of the data required here? Because I'm having 200 to 250 MRI images, and every fruit is having 18 slices. So you can say 250 into 18 can be my data.
Okay.
So is this data sufficient for my work?
If you are going with the machine learning, then the number of records, even though it is less, it is not a problem. But in case of deep learning, you need a huge amount of data, because only with the help of a huge amount of data it will predict or if your loss function will be evaluated accurately.
So in that case, see, if I'm having a fruit of a known harvesting time, if the harvesting time is to be very much fixed, I have to go for a very less number of, like I can't go frequently to have the fruits. So 250 fruits I have taken of a particular harvesting time, and
Uh,
that I'm trying to predict the freshness of the fruit. from the work.
Or else you can also go for another method called a data augmentation, where your images can be, you can duplicate your images. Okay.
Okay. So with the data augmentation, I can apply CNN in this, sir?
Yes, 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 yes.
Okay. So that may not be a problem while declaring the like accuracy and all the details that is required for the research.
No, no, no. The
Okay. Thank
purpose
you
of,
so much, sir.
yes.
Thank you so
Oh,
much.
yes, Prajesh. Yes, Prajesh. Yes, Prajesh. Prajesh.
Sir,
Yes,
you can
Prajesh.
unmute and talk, sir. Sir, you have been allowed to open the mic, sir.
Any questions?
Sir, you have been allowed to speak, sir. Unmute your mic, sir.
Brijesh Lal, do you have any questions? Brijesh Lal, do you have any questions? Yes, Pooja.
Sir, good
Yes.
afternoon.
Good afternoon, ma'am.
Sir, I wanted to know that how the kernel selection can be done, like depending upon different application. Is it like we need to study about the kernel initially to do to attain the required result, or is there any specific method for it?
In CNN, kernel will be selected automatically, and this will be done during the back propagation.
Oh, okay, sir. Okay, okay. It is selected automatically in the
Yes,
sense
yes,
like,
yes.
okay, depending upon,
Suppose,
yes, sir.
suppose during the convolution layer, we are including the filter size. We are including the number of filters as 32, right? So this 32 means it will create randomly. It will create 32 filters of input depth size, so that it will calculate it will calculate the weighted sum, and it will predict the output. And if the prediction is wrong, then automatically the optimizer will do back propagation to update these weights in the sense update these filters weights.
Okay, okay, fine, sir. Sir, one more thing. If we create a neural network, a CNN, the number of hidden layers, like, will it be done automatically, or can we give how many hidden layers are required by us? And
Uh,
whether the accuracy will increase if we increase the number of hidden layers?
It all depends upon the data set as well as it is an experiment, ma'am, because the number of hidden layers and the number of depth of the hidden layers, or else the number of units or number of filters and the size of the filters, all are hyperparameters. We need to sit and we need to experiment one by one.
Oh, okay, sir. Okay, sir. Sir, can I ask one more thing? Sir, if I was working with PatternNet for image recognition, so is it a better option, or are there any other options for image recognition?
So in image recognition, CNN will work fine with the images. In order to find we also have some different kinds of CNN like RNN, and we have some varieties of different convolution networks.
Okay,
You
sir.
can also try it out.
Okay, ma'am. Okay, sir. Sir, then PatternNet, is there any more information about PatternNet? Because I was searching for it, but I got only very limited. Have you gone through it, sir? PatternNet neural network.
I have not gone through that pattern neural network. Anyhow, you send me a mail, I will reply for that. Okay.
Okay, sir. Can I get your mail ID, sir?
Joseph
Joseph
George
George
dot
dot
mtech
mtech.
at
Okay, sir.
at gmail.com.
Sir, it is mtech, no?
Yes, yes,
Sir, everything small, yes.
yes, yes. Everything is smaller.
Sir, if possible, can you provide your contact number, or shall we correct from the organizers?
Yeah, you can collect from the organizers.
Okay, sir. Thank you. Thank you so much.
Participant, if any doubt, any more doubt?
Hello, sir. Myself,
Yes.
Priyanka. Sir, am I audible, sir?
Yes, ma'am. Yes, ma'am.
Yes, sir. Sir, I am also working with CNNs, sir.
Okay.
So usually, whenever we want to optimize hyperparameters, is it a better way to use optimization algorithms, sir? But it's very difficult. I'm finding it very difficult to use optimization algorithms in order to tune my parameters, sir. George, sir.
Joseph, sir?
Yes, yes. We also have optimization tuning techniques.
Yes, sir. So how can we proceed with that, sir? Just like randomly we can fix some filters and we can design an CNN and we can test with multiple parameters variations. But when we see most of optimization algorithms like ANT
You are
algorithm,
using
Firefly algorithms.
build defined optimization technique only you can use, right? Yes, ma'am.
Yeah, sir.
Yes, ma'am. You according to the your input, you can change your optimization technique, right? You get the how much
Yes.
output accuracy, right? Then only you decide, right?
Yes, sir.
Yes, yes, ma'am. Actually, you keep on changed your optimization technique. You find out which optimization session technique optimal for accuracy for your project. You check it, then you
Yes,
can
sir.
use it, ma'am. That's the rule, right?
So one more question, sir.
Yes,
Sir, usually I am working with single CPU, sir, but I don't have GPU processor, so CMS will be very slow now, sir, in single CPU. What else I can do, sir?
how much your data set, ma'am? How much size of your
Data
data
set
set?
is of only 500 or 1000 images, sir.
It's enough, ma'am.
It's
500
enough, sir.
image set is very very small one.
Yeah, 1000 images if it is there.
Uh,
Then with single CPU, it may take long time, no, sir. So any like
if you suppose if you want you have using more data set means you request to me and or otherwise my MA team, right? So our colleagues also provide to the some cloud system, right?
yeah, sir. Is it possible, sir, with MATLAB? I work with MATLAB coding.
You are working MATLAB.
Yes, sir. Okay. So in the cloud, will I be able to access GPU processors, sir?
Seriously, I am not working with MATLAB.
Okay.
Only printed out paper mail. Joseph sir, can you tell?
Ma'am, you can. I am also not working with MATLAB, but there are service providers who provide clouds. You can request for GPUs, and it depends upon the capacity and depends upon the number of GPUs. It may vary.
Yes, ma'am. That's why
Okay.
I told we are provide some cloud options, right? If you want, you
Okay.
request to our college, right?
So how to contact with you, sir?
I think you go to my college website, some contact mail IDs there, or otherwise you are using my mail ID, right? So V.d.Ambeth@panimalan.ac.in. You send to me request, I will forward to my higher authority.
Yes, sir. This ATAL FDP mails what we're getting. Can I contact
Yes,
with
ma'am.
you, sir?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Okay. Thank you. Thank you so much, sir. It would be a great help. Thank you, sir.
Yes, ma'am. Thank you. Thank you.
Okay.
Participant, if any doubt, any more doubt? Okay, if you any doubt, you come to the, you put in WhatsApp group also, right? We have rectify in future also, right? Okay. Once again, I will thank you for your valuable session, sir, Dr. Mr. Joseph, sir, right? Thank you very much. You are accepting my invitation, right? Once again, I will thanks to you and all the participant also, right? You are cooperate with me, right? Today assignment questions I will put in on the WhatsApp group, right? After 15 minutes, right? Okay, thank you to all.
Okay.
Sir, please. Sir,
Yes,
we are
ma'am.
not. Sir, how
Yes,
I
ma'am.
don't know. We are not into WhatsApp group, sir. From yesterday, I'm putting in the text box.
Yes,
In the
ma'am. You put in separate text me, right? In WhatsApp, I will put the link, right? Okay, ma'am.
your WhatsApp number, sir.
So 866
One second, sir. I'm noting down. 866
70
70
80
80
877.
877. Sir, I
Yes.
repeat 866 877.
Yes, ma'am. Yes, ma'am. Right.
Okay,
So
okay. Thank
you
you, sir.
just put one message, a text message. I will immediately give it to the link. Right.
Yeah. Yes, sir.
Okay.
Thank you, sir. Okay. Okay,
Thank.
sir.
I think wind up this session. Right.
Okay, sir. Thank
So
you, sir.
any more doubt? Thank you very much, sir.